Imagine a universe dominated by a mysterious force that pushes everything apart. This force is so powerful that it affects every corner of the cosmos, stretching the very fabric of space itself. This is the essence of the De Sitter universe, named after Dutch astronomer Willem de Sitter. His groundbreaking work in the early 20th century laid the foundation for our understanding of this unique cosmic model. Unlike our universe, filled with matter and energy, the De Sitter universe is largely empty, driven by the cosmological constant. This constant acts as a repulsive force, causing the universe to expand at an accelerating rate. This concept might seem strange, a universe expanding forever without stars and planets. It's a stark contrast to the vibrant, dynamic universe we inhabit, filled with galaxies, stars, and planets. However, the De Sitter universe has profound implications for our understanding of cosmology and the fate of our universe. It challenges our perceptions and forces us to rethink the ultimate destiny of everything we know. By studying this model, we gain insights into dark energy, the force accelerating our universe's expansion. Dark energy remains one of the greatest mysteries in modern physics, and the De Sitter universe provides a crucial framework for exploring its properties. One intriguing aspect is cosmological horizons. These horizons represent the limits of what we can observe, as the universe expands faster than the speed of light. Imagine standing still while the ground beneath you expands exponentially, making distant objects disappear from view. This phenomenon illustrates the mind-bending nature of the De Sitter universe. The De Sitter universe, with its relentless expansion, is a place where even light can be outrun by the expansion of space. This relentless expansion paints a picture of a universe that is ever-growing, ever-changing, and ultimately without end. The story of the De Sitter universe begins with Albert Einstein. In 1915, Einstein published his theory of general relativity, revolutionizing our understanding of gravity. Gravity was no longer a mysterious force but a manifestation of space-time curvature, warped by mass and energy. Einstein believed in a static universe and introduced the cosmological constant to achieve equilibrium. Willem de Sitter, in 1917, found a solution to Einstein's equations describing an expanding universe. Instead of galaxies flying apart, space itself was stretching, carrying galaxies along. This expansion was accelerating, driven by the cosmological constant. De Sitter's universe was a radical departure from the static cosmos. It took Edwin Hubble's observations to gain acceptance for the idea of an expanding universe. To understand the De Sitter universe, we must delve into Einstein's equations and the cosmological constant. These equations, formulated by Albert Einstein, are the cornerstone of our understanding of the cosmos. They describe how matter and energy interact with the fabric of space-time, shaping the universe as we know it. Represented by the Greek letter lambda, it signifies energy inherent to the vacuum of space. This energy is not something we can see or touch, but it has profound effects on the universe's structure and behavior. Unlike matter and radiation, which exert gravitational pull, the cosmological constant acts as a repulsive force. This means it pushes things apart rather than pulling them together, counteracting the force of gravity. Imagine a rubber sheet representing space-time, with a heavy ball causing it to sag, creating a gravitational well. This is how gravity works, pulling objects towards the center of the well. Now, imagine the sheet imbued with energy that causes it to expand outward. This energy stretches the sheet, making the well shallower and pushing objects away from the center. This outward push is akin to the effect of the cosmological constant. It acts uniformly across the universe, causing space itself to expand. In the De Sitter universe, the cosmological constant reigns supreme. It dominates over all other forces, dictating the universe's expansion. With no matter or radiation to counteract it, lambda drives exponential expansion. This means the universe grows at an ever-increasing rate, with galaxies moving farther apart from each other. Distances between galaxies increase at an accelerating rate. This acceleration is a key feature of the De Sitter universe, making it vastly different from our current understanding of the cosmos. The universe grows larger, not because things move through space, but because space itself is stretching. This stretching of space is a direct consequence of the cosmological constant, reshaping our understanding of the universe's fate. One consequence of the De Sitter universe's expansion is the creation of cosmological horizons. These horizons represent limits on how far light and information can travel in expanding space-time. Imagine a beam of light from a distant galaxy traveling towards an observer. As the light travels, space between the galaxy and observer expands. In a de Sitter universe where expansion accelerates, there comes a point where space expands faster than light. The light from the distant galaxy will never reach the observer. The galaxy effectively disappears beyond the observer's cosmological horizon. This horizon is a constantly expanding sphere centered on the observer. More of the universe disappears beyond this horizon, forever inaccessible. While the de Sitter universe is a fascinating theoretical framework, our universe is not a perfect de Sitter universe. Our universe is filled with matter and radiation, from subatomic particles to galaxy clusters. These constituents exert a gravitational pull that counteracts the cosmological constant. Our universe's expansion history is more complex than the simple exponential expansion of the de Sitter universe. For billions of years, the expansion was slowing down due to gravity. However, in recent years, the cosmological constant has taken over, and the expansion is now accelerating rapidly. The de Sitter universe has profound implications for fundamental questions in physics, particularly in our quest for a unified theory of everything. This concept challenges our understanding of the cosmos and pushes the boundaries of what we know about the universe's structure and behavior. One area of intense debate is string theory, which attempts to reconcile quantum mechanics with general relativity. String theory proposes that the fundamental particles we observe are actually tiny, vibrating strings, each with its own unique frequency. However, string theory faces a significant challenge in accommodating the accelerated expansion of our universe, a phenomenon that the de Sitter universe explains. This accelerated expansion is driven by what we call dark energy, a mysterious force that makes up about 70% of the universe. The de Sitter swampland conjecture suggests that universes with a positive cosmological constant, like ours, might be incompatible with a consistent theory of quantum gravity. This conjecture implies that our current models may need significant revision. If true, this conjecture would have profound implications, potentially ruling out vast classes of cosmological models. It would force scientists to rethink the fundamental principles that govern our understanding of the universe. The debate highlights the deep connections between cosmology, particle physics, and the search for a unified theory. These fields are intertwined, each providing crucial insights that help us piece together the grand puzzle of the universe. The de Sitter universe has emerged as a crucial testing ground for our most ambitious theoretical frameworks. It serves as a cosmic laboratory where we can test the limits of our theories and explore the fundamental nature of reality itself. The de Sitter universe offers a glimpse into a possible future for our own universe. As the cosmological constant drives accelerated expansion, our universe may enter a de Sitter-like phase. Galaxies will continue to recede, their light becoming increasingly redshifted until they disappear beyond our cosmological horizon. New stars will form, but they will be confined to our local group of galaxies. The rest of the universe will become increasingly dark and desolate. However, new discoveries could alter our predictions for the universe's fate. The study of the de Sitter universe allows us to explore the vast range of possibilities that lie ahead. By studying the de Sitter universe, we embark on a journey to unravel the deepest mysteries of the cosmos.